So today we are going to start talking about polynomials and their graphs and how to solve them. And so we may not have put a name to them already, but we've already been working with polynomials. We actually really like working with polynomials in calculus because they're one of the easier types of functions to work with. But we've already been working with this particular type of function. I've just got y equals x minus 3, which is a linear function. And also quadratic functions are also polynomials. So some things that make these polynomials is one, there are no non-integer coefficients. So what that means is that, or exponents I should say. So what that means is that all of my exponents are positive whole numbers, okay? There's no negative exponents, there's no fractional exponents, so it's all very nice. So when I multiply this x minus 3 quantity squared out, this is like the quadratic polynomial x squared minus 6x plus 9. Right? I just have it kind of factored here because we're going to talk about that. But one of the nice things about that you're going to notice when I start graphing these that I want to point out is that polynomials have these beautiful smooth graphs. There's no sharp bends like in the absolute value type of graph, and they're just like nice and continuous, meaning I can draw them without taking my pen off the paper, graphs, okay? So that's one of the nice things with them. So I want to point out some different characteristics. So the most basic one is my linear. I'm not really going to talk about linear anymore, but this is a first degree polynomial because the highest exponent on it is a 1. So a quadratic function is what we call a second degree polynomial. It kind of goes with the exponent. The highest exponent is a 2, right? If I multiplied this out, I'd have x squared minus 6x plus 9 again, right? And so my largest exponent is a 2. That makes it a second degree polynomial, which we fondly call it a quadratic function. Okay. So quadratic functions with positive leading coefficients here, right? If I put a minus in front of any of these, the only thing that it does is changes the direction that it opens, right? So I'm going to show occasionally the negative version, but when I want to really, I'm just kind of going with the positive version right here. So a quadratic could look like this with one factor squared, or it could look like this where I have the two distinct factors, right? I can kind of tell still that this is a quadratic. One, if I factor it out or multiply it out, this would be x squared minus 5x plus 6. But what I want to see is basically the number of factors that I have here is basically the degree. So I have, even though this is 1, it's showing up twice, right? So this is a 2, right, factors, and this also has 2 factors, making a quadratic. So something that I want to point out that we're going to talk in more detail on the next video or lecture is that when I look at this one here, I only have the one factor squared, and what I find here is that I'm not actually crossing the x-axis here. I kind of bump into it and turn back around, okay? So that's just something I want to point out. I'm going to talk more in detail about it in the next lecture. So now here I get 2 distinct factors, right? Each one is different, and if I set them both equal to 0, I get x equals 3 and x equals 2. I notice here, right, these are the places where I'm crossing, and I get crosses at both of those. We're back here, right? Oops, got the wrong one. Getting ahead of myself. My 1x, right, if I set the x minus 3 equal to 0, I get x equals 3. So I just have the 1 x-intercept here. All right, so those are the 2 types of quadratic functions that I can have. Either it's the same factor squared, or I get 2 distinct factors that I multiplied together. So I want to point out this is an even exponent function, and my end behavior matches, meaning when I come up, right, basically I'm kind of thinking, okay, well, it means I'm starting and finishing in this direction, okay? So if I put a minus sign here again, if I put that back in here, minus here, and then I'll put one here, then I still have this, what we call matching end behavior, okay? So this time they're both dropping. Okay, so that's just something I wanted to point out there. All right, so let's look at another polynomial, and we've worked with this one before as well. This is an x cubed polynomial, right? You should know before I even graph this, that this is the graph of x cubed, shifted 3 to the right because I have y equals x minus 3 quantity cubed here, right? I'm working with this one right here. And so it's just x cubed shifted to the right. So there's multiple ways that this can also present itself, but I'm going to put the minus here just to get the, right? That's what happens when we put the minus. It's just a reflection. We usually say that that's a reflection over or into the x-axis. But this is my standard cubic polynomial, okay? And this has 3 factors, right? Now I have them all 3 showing up as 1 here, or if I have, again, 3 factors here, right? I get x minus 3 squared, so I'm dealing with this one here, times x minus 1. So I get an extra sort of little wrinkle in my graph here, right? So, but this is also an x cubed, but I do want to point out that my end behavior, again, just like this one up here, my graph starts in one place and ends in the other. Starts in one place, ends in another. This has an extra little bump in it, but still a cubic polynomial. So this is one example. One more thing let me talk about real quick when I come back here. I want to talk about both of these quadratics just has what we say is a turning point, right? We kind of talked about relative max and mins somewhere. So this one has a relative, or actually this one's an absolute maximum, but it sort of has this max point here. And if I take away the negative sign, then it has a min point. But in both cases, this quadratic only has this one turnaround point. We call them turning points. Okay. So when I come down here to x cubed, this one just has, it really doesn't have a turnaround point, right? That one's just like one continuous sort of smooth. It kind of pauses there, but it doesn't really have a turnaround point. But if I look at this next cubic function, where I've got x minus 3 squared and x minus 1. So these are my, when I set these equal to 0, I find that these are where my function is hitting the x-axis, right? They're my x-intercepts. So at x equals 3 and x equals 1, I get x-intercepts, and I do, right here and here. Let me make them. Now I want to point out something here that, remember when we had this quadratic up here that was x minus 3 squared? It was like a bump into the x-axis. Again, I have this x minus 3 squared, and I'm getting that bump again, right? It's not actually crossing over the x-axis. It bumps into it and turns around. But then at x equals 1, I do get the crossover, right? But again, I'm starting down here and finishing up here in opposite behavior. And if I put a minus inside, then I have the opposite behavior. But again, it's starting and finishing in opposite directions. All right, so let's look at another one. So right now, this one has 3 distinct factors. Now, if I look at this, can I click on this to make it? Okay, so this one has x minus 3, x minus 1, and x plus 3. Even without multiplying this together, right, I can multiply this all together. I know that I'm going to have a cubic polynomial because I have 1, 2, 3 factors. Right, so that makes it a 3rd degree. Now when I look at this one, I'm going to back up here. Let me back up a little bit. Now this one actually has 2 turning points. Okay, so I've got this turnaround spot here. Basically it means where I'm going either from increasing to decreasing or decreasing to increasing. So I'm increasing here, and then I'm decreasing, and then I'm increasing. So this has 2 turnaround points here, here, and here. Okay. If I go back to the previous one, that only had 1. No, actually it had 2, sorry. Let me take away these points so we can see it a little bit better. But I have 1 here and here, okay? So I'm kind of trying to point this out. If you notice, the quadratic polynomial had 1 turnaround point. The cubic polynomial can have 2 turnaround points, okay? All right, so let's move on to x to the 4th. X to the 4th now, x minus 3 quantity to the 4th. We haven't dealt with this one at all, but it looks very much like a quadratic, right? It looks very much in a shifted way. When I have the same factor showing up 4 times, it looks just like a quadratic, except it's a little flatter down here at the bottom, but very similar to a quadratic. And I would like to point out also that it's starting and finishing in the same direction. And just like a quadratic, if I put this minus sign right here, then I'm going to start and finish in the same direction. They're both down instead of both up. Okay. Oops, so let me take away that minus again. So let me show you all the way that fourth degree polynomials can present themselves. Okay, so this one just has one turnaround point because it's got 4 distinct factors. Also, I would like to point out that this is a bump as well. And so there's a connection here between the number of times that the factor shows up and when I get this turnaround versus when I get the cross. So we're going to talk about that more in detail in the next lecture, but I'm just kind of pointing it out. All right, so now this one is a fourth degree polynomial as well. I can tell because I have 4, right? This one is showing up 3 times, but I have 4 factors that are linear that are showing up. So this is a fourth degree polynomial. This one's kind of an interesting, right? Again, I'm going to get a cross at x equals, or an x-intercept at x equals 3 and x equals 1 when I set each one of these factors equal to 0, which I do here, right? There's 1 and there's 1. So the other ones, if you notice, on some of them, this is like nice and sort of symmetric right here. It like comes down and crosses and it's perfect. Where this one sort of has this extra little bend to it. That's what happens when I get higher factors here. It comes from the x minus 3 cubed. All right, so this one has 2 x-intercepts. And again, if I put the minus in front, all it does is flip it down. It keeps its same shape. It just moves it down. Now this one has 2 distinct, right? This one also has 2, but I get squared and squared. So this one, let me back up a little bit. I kind of think of these as, it sort of looks like a big W. Oh, this one's really hard to see. It's going to get really smushed. But you can kind of see it comes up, it goes down, it goes up, it goes down. It's sort of like a W. So fourth degree polynomials can sometimes take on like sort of that W shape. W if I've got a leading coefficient that's positive, or an M if I flip it upside down when I put the minus sign in the front. Right, like this. Oops, it went way down. Let's look. There it is. Okay. So it keeps its same shape. It's just downward instead of upward. And if I go back here to the positive, notice that, oops, that here, let me blow this up a little bit. Doesn't matter if we can't see the rest. I'm just trying to show you the x-intercepts here, right? At 3 and -2, when I set the 2 factors equal to 0, that's where my x-intercepts happen. I get that since they both have a power of 2 on them, I'm getting this bump behavior, right? They're not actually crossing over. They are bumping in and turning around. All right. All right, so that was 2 ways that the fourth degree, right? So then I can also have this, where this one has 3 distinct factors now, right? So I have x minus 3 showing up twice, and an x plus 1 and an x minus 1. So from this x minus 3, I get x equals 3. That's this point here. I get x equals -1 from x plus 1, which is here. And then I get x equals 1 from that last factor, which is x equals 1. So I get these 3. I still have that sort of W shape to it, right? It's just a little interesting W. It's got a little bit longer end than the other does. But again, now this one has 1, 2, 3 turning points, as this one only had 2. Actually, no, it does. It have 3. I just can't see the one that's up here. And then this one also, this one just has the 1 turning point. So then the last one is 4 distinct factors. Okay, so this one has x minus 3, x plus 1, x minus 1, and x plus 3. I can tell it's a fourth degree because I have 4 linear factors. And this one is the classic looking W here. So it looks like this. Again, it has 1, 2, 3 turning points. Basically, it's decreasing. It hits this bottom piece here. And then it's increasing here, it hits this top piece, it turns around, so I have turning points here, here, and here. Okay, so it has 3 turning points. Now if I kept going with these, right, and in here we're mostly going to talk about up to fourth degree, but these polynomials follow the pattern. when my degree is even, meaning if I go 2 and 4, right, this is a 4. If I went to 6, then I still have this n behavior that matches. It goes up like this, right? Or if it's got a negative in front, then they both fall. Let me do that. So that applies to x to the 6th, x to the 8, and so on. Where if I have an odd polynomial degree, let me find an odd degree here. How about this one here? Then think in terms of x cubed, right? When the leading coefficient is positive, then I have this sort of opposite, right? Here I'm rising, here I'm sort of falling back here. So there's opposite behavior. And so if it's a positive leading coefficient, if I have x, even linear equations, right? Linear equations that have positive slope, they just rise and fall like this in the same direction as this one does. So if I have x to the 5th, it will also be down here and finish up here. It'll have extra bumps in it, but it'll still be up here. And that will happen for all odd. And then the opposite, when I put the minus in front, right, instead of when it's even, I get the down-down behavior, then I just get the opposite. Then I fall from the left and keep falling, but I'm in opposite directions again. Okay. Also, I kind of was pointing out turning points, but the turning points essentially go with the degree of the polynomial. So basically the degree of the polynomial, like here I had the squared, right? So this is degree 2, and I had one less turning point. I have 1. So in all of these, the degree of my polynomial I can have at most n minus 1 turning points, meaning that's where I'm turning around and changing from decreasing to increasing or increasing to decreasing. Also, I can have at most, so if I have a quadratic polynomial, I have a degree 2, I can have at most 2 x-intercepts. Usually we call them solutions because in most cases when we're solving polynomials, we set them equal to 0 and factor them. And so the number of solutions or x-intercepts that a polynomial can have goes up with the degree. So a 4th degree polynomial that we looked at can have up to 4 possible solutions. This last one is the one that has the 4. Let me take these off. Right, so this one has, because normally what we do is we set them equal to 0 and we factor them. And so basically we have these 4 distinct solutions when we set it equal to 0, or 4 distinct x-intercepts. So a polynomial can have, of degree n, can have at most n minus 1 turning points, so 1 less turning point than its exponent, and we can have up to n solutions. So degree 4 can have 4 possible solutions, a degree 2 can have at most 2, and so on. Okay, we will talk more about polynomials in the next lecture.